Okay, well, the previous presentation has already shown that information about the derivative can give us information about the function, and in fact it turns out that certain easy-to-solve problems for the derivative, such as finding whether the derivative is equal to 0, can give us information about problems that are harder to solve for the function, namely where there would be relative maxima or minima. Now we have to be careful with that, because sometimes a derivative can be 0 and the function can just have a saddle point. It can look like something like f of x equals x cubed. And so it sounds like a good idea to further investigate the relationship between the function and its derivative, and that's what's happening here. Let's go. Okay, so how do we connect the function with its derivative? The underlying idea is that, or the underlying desire maybe is that now that we know where to look for local extrema or turnaround points, it would also be nice to be able to say something about the growth behavior of the functions, and growth behavior always means where the function is increasing or decreasing. But the definitions of increasing and decreasing functions, which we'll also restate in this presentation, those are hard to use. So it would be nice to have a simpler characterization of growth behavior, maybe in terms of derivatives, of course, a priori or without further information. We'd just like to have any simpler characterization, but it turns out that a characterization in terms of derivatives is the standard one to work with. Okay, so first of all, we should convince ourselves that such a characterization actually should exist. And here's where I'm just going to take a look at a graph that wiggles around quite a bit, and I'm going to slide a tangent line along that graph. And you can see that basically whenever the function is decreasing, whenever the function is going down, the tangent line of the sliding point is pointing downwards. And whenever the function is going up, as it's going to be in just a minute, then the slope of the tangent line is pointing upwards. So it seems that for a differentiable function, positive slopes should be connected to, or positive derivatives should be connected to increasing, and negative derivatives should be connected to decreasing, and that is indeed the case. But we would, of course, need to have a formal proof of that. So similar to the end of the previous presentation, we're going to talk a little bit more about formal justifications here. So let's see. Basically, the questions we could ask is, if all slopes on an interval are positive, how could the function itself not be increasing? Similarly, if all slopes are negative, how could the function itself not be decreasing? Well, the formal justification takes a little bit longer, but we also do need a formal justification to progress without any unforeseen consequences, because certain conclusions just look really tempting. But remember, the Earth isn't flat either, right? Even though locally it looks as if it is rather flat. I mean, I've driven through western Kansas, I've lived in Kansas for a while, that looks rather flat, and yet the Earth is not. Okay, so the connection that, or the theorem that makes the connection between the macroscopic idea of growth behavior and the microscopic behavior of derivatives is the mean value theorem. So let's take a look at that, and first we need to talk about the derivative really as a function. If f is a function and d diff is a set of points where the function is differentiable, then we can define a function on that set, and that function should map every point to the derivative of the function at that point, and that function is called the first derivative of f, and of course we will call that derivative function f prime too. Then if we have a function, we can also talk about whether the function is strictly increasing or decreasing, and a function is strictly increasing in the interval if and only if for all x1 and x2 in the interval, where x1 is less than x2, we have that f of x1 is smaller than f of x2. Basically, as we go from left to right, our values are supposed to go up. That's the idea of increasing. The function is called strictly decreasing if and only if for all x1 smaller x2 in the interval, we have that f of x1 is greater than f of x2. And these definitions, I would conjecture they're biased by the fact that in the Western world where these concepts were developed, we are writing from left to right. So for us, if we go from left to right and the values are going up, we perceive that as increasing. If we're going from left to right and the values are going down, we perceive that as decreasing. It may well be that in a culture in which people write from right to left, it would have been exactly the opposite, because people would consider it more natural to go from right to left through a graph. But this is the definition that came out in the original invention, and that's the definition that has stuck with people. The other thing we see about this definition of increasing and decreasing is that just as the definition of extreme values in the previous presentation, it is very cumbersome. The only way we can work with this definition is if we already know where we think the function is increasing and decreasing, and then, well, then we could verify that that is the case, but that verification is actually the verification of an implication. If x1 is smaller than x2, then f of x1 is smaller than f of x2, and not only is it an implication, it's an implication that involves inequalities which are rather unhandy to work with, and which we're most likely not used to. So even though this is the right definition, even though this is a good definition, it sounds like it would be nice to have something that is simpler, and that's of course where the derivative function comes in. Namely, here's the mean value theorem, which is a preparatory stage towards talking about growth behavior. You take a function that is continuous on the closed interval and differentiable on the open interval. That's a technical hypothesis that we need for the abstract proof. We're only going to give a sketch here again, but it is the correct hypothesis. The mean value theorem says that then there is a number c between a and b, so that f of b minus f of a divided by b minus a is equal to f prime of c. So that means that on any interval where the function is differentiable, the slope of the secant line from that is defined by the endpoints is equal to the slope of the derivative of some point within the interval. Now that looks very, very abstract, and that's because it is, but basically what this theorem does is it takes a macroscopic concept, the slope of a secant line, which then also can be used to talk about increasing and decreasing, because we've got f of b minus f of a, which of course does connect to these inequalities that we had on the previous panel. It takes this macroscopic idea and connects it to a microscopic idea, which is the idea of a derivative. Okay, the idea for the proof is that, well, for f of a equals f of b, this is just Rolle's theorem, because Rolle's theorem, f of a equals f of b, you get a 0 on the left side, and you get f prime of c equals 0. And the proof itself then is basically, basically the mean value theorem is Rolle's theorem on a slope. And for an abstract proof, you would just subtract a straight line of the slope f of b minus f of a from f to obtain a new function g. That function will have equal values at the endpoints, so that means that this function can, for this function we can apply Rolle's theorem, and we get g prime of c, and when you translate that back to a result for the derivative of f, you end up with f prime of c being this thing here. So this is something where you may want to use these ideas and reread the proof in your book, or maybe even try to work out the proof for yourself. I'm not going to go into the details here. The visualization of the mean value theorem is that, well, you've got a function that somehow wiggles around. You've got a starting point a, you've got an ending point b, you've got a secant line that goes through a f of a and b f of b, and we can already see in this picture there's got to be some kind of tangent here that's got to be parallel to the secant line, and the mean value theorem simply says that yes, the existence of such a tangent line is guaranteed, and well, there may be more than one, so there's one here at C1 and another one at C2. What the mean value theorem says is there's at least one of those tangent lines, and that's going to be good enough for us to make the connection between growth behavior and derivatives, which is exactly where we're headed next, namely that f be a differentiable function in the interval ab, the open interval, and that it be continuous in the closed interval. Remember that it's this standard technical hypothesis that really can only be fully justified if you're going through, or fully justified in detail in an advanced calculus class, but it is the right hypothesis. If the derivative is greater than 0 for every x in the interval ab, then the function must be increasing on the closed interval ab. And, well, how do you prove that? Well, suppose for a contradiction that the function is decreasing somewhere. Well, if the function were decreasing, then there's got to be some point A, some starting point A, and some ending point B, where the function actually violates the idea of being increasing. That means you'd have to have a place where you go from the left to the right, and we just happen to call these things A and B. They don't need to be the endpoints from the previous slide. So it's such that f at the left end is greater than f at the right end. Well, the function is continuous, which means the function must still somehow link up these 2 points. Well, that still isn't quite the contradiction, but then by the mean value theorem, we know that this negative slope of this secant line must be replicated somewhere as a negative slope of a tangent line at some point c within the interval. And here's where the contradiction for the mean values for the proof is, because we had said the function is differentiable with positive slope everywhere in the interval, and this slope here is negative. So that would be a proof by contradiction that positive slopes give you an increasing function. Similarly, by just reversing the right kinds of inequalities, you get a theorem that says negative slopes give you a decreasing function. Okay, yeah, here, take again this technical hypothesis that we always have. If the derivative is always smaller than 0, then the function is decreasing on the interval. Okay, now, basically what we take out of this is positive slopes means increasing, negative slopes means decreasing, and that means we can make a graphical connection between a function and its derivative. And a very standard way to do that is to just take a function graphically and sketch its derivative. Now again, these are estimates, so we're not going to get the exact derivative of this function sketched, but we're going to get something that is pretty close to it. And the way to do that would be, well, you just sketch yourself some axes right underneath the graph that you are given. And what I would always want to focus on are where the slopes are 0. So the function has slope 0 here, and that means the derivative must be equal to 0 in this place. The function has slope 0 here, which means that the derivative must be equal to 0 here. The function has slope 0 here. That's I mean that to be slope 0. That's something where you have to look really carefully, or look at a symbolic definition of the function, but the slope is supposed to be 0 here, and that gives us a derivative being 0 here, and that means the derivative just has to wiggle through these 3 points somehow. And how does it do that? Well, the function is increasing up to this first 0, which means we must have a positive derivative. But because the slopes are first steep and then getting less steep until they end up being 0, the derivative comes in like something like this probably. Then the derivative will be negative from this point to this point because the function is decreasing. And of course it comes out with a very small negative derivative, then gets steeper, and then turns around and gets less steep. So it first gets a larger negative derivative up until we reach the place where the slope is steepest, which is about here. And then it turns around and comes back to a 0 derivative. Now from here to here, the function is increasing, so the derivative should be positive. Steepest slope is somewhere around here. So we get positive slopes that get larger and larger up until here. And then the slopes get smaller until we hit 0 again. That's where I had to bend really quick. And this time around, we have a saddle point. Remember, 0 derivative doesn't necessarily mean that you've got a turnaround point. So here we've got a positive slope, and we continue with positive slopes, and that means the derivative remains positive and just goes out like this maybe. Now this is just a qualitative way to get the derivative, but it can be pretty accurate if you estimate these points, right? And other than that, of course, the idea behind these problems is just for us to make the connection between the derivative and the function. Now this is the way to make the forward connection. You have the function, you want to find the derivative. Well, you can also go backwards. You can have the derivative given, and you want to find the graph of the function. And in order to do that, well, here's the derivative. Get yourself some axes that you label, okay, x and y, and you want to have the graph of the function f. This time around, well, the zeros of the derivative are where the function turns around, right? So this time we can just mark the places where the function has to change from increasing to decreasing or from decreasing to increasing. And, well, we don't quite know how high or how low the function ends up, so we can just take an arbitrary starting point, actually, unless a starting point is given, which can also happen in these problems. And, well, we start out with negative slopes, so the function must be decreasing, and it is. Then we get positive slopes, so the function ought to be increasing. Steepest slope is around here, so the function increases, gets its steepest slope, then turns around, gets back to slope 0. Then the function has a negative derivative, which means it's going to decrease, assume its steepest slope actually for a while. So it first decreases, and then it's got constant slope. Well, a constant slope is just a straight line. Then the slopes turn around to being 0 again, so we end up with another turnaround point. And then the function is increasing one more time. Now, the process of recovering a function from its derivative. That's called integration, and there is one ambiguity in that, which we're also can see graphically here, and that is nobody told us to start at 0 here. I could have started higher up. I would have gotten the same shape, just a little bit higher up. So as you do this problem, unless somebody tells you that this thing has to go through a certain kind of point, you just start somewhere and draw the correct shape. Okay, with that, we can talk about extrema one more time, because what we've seen is that basically an extremum is where you change from increasing to decreasing, or from decreasing to increasing. And so that is something that we can also work out here. Again, for extrema, we need a little bit of wiggle room to the left and to the right. We don't necessarily need that the function is differentiable at a, but it needs to be continuous there. And now if the slope is greater than 0 to the left of a, and if the slope is smaller than 0 to the right of a, and this is really something where I often just start doing shadow boxing. Let's see, a is in the middle, slope is greater than 0 on the left, smaller than 0 on the right. That means there's got to be a maximum there, because the function just went like this, right? And, well, that is something that can help you remember these kinds of theorems. And, of course, there's another part to that, or, well, no, there's not another part to it, but basically, if you change from negative slope to positive slope, well, then there's got to be a minimum. Okay, a point is called a critical point of the function if and only if the derivative is 0 or if the derivative is undefined. Well, how does that go? Well, we've just seen that when the derivative changes its sign, that is a local maximum or a local minimum. And, well, of course, if that is the case, then we can go back to what we've done for the intermediate value theorem, and we know that a function changes its sign if and only if it's 0 or undefined in a place. And so those are exactly the places where we could have a maximum or a minimum. And, yeah, that's already it. These kinds of critical points will stay with us in our investigation of derivatives. And basically, we will always find them by finding zeros and where the derivative is undefined. And then we're either doing a sign analysis, like in this theorem, to determine where the function has its local maxima or its local minima. The next presentation, which is also the final presentation in this module on the conceptual introduction of the derivative, will tell us a little bit more as to how we can do a more refined analysis of the shape of the function, which is something that is useful in sketching graphs by hand, which is a neat little skill to have, but it is also useful in the analysis of trends of where a function might go. All right, until then.